So what we're going to focus on today is kinetics of chemical reactions. So when we talk about kinetics, we're really talking about the rates of a given reaction. So you're going to hear the term rate used a lot as we're discussing this here, okay? And kinetics will be the rate at which a given reaction occurs. So we're kind of moving a little bit away from equilibrium here. Equilibrium would still have a kinetic rate. However, a lot of these individual examples are not necessarily going to be shown at equilibrium. But I don't want you to think that equilibrium doesn't apply here. We would certainly have rates of reactions at equilibrium. So we're going to just take a general example to start, which is, let's consider a reactant A that is over time producing some product B. So the way that we can view this from a kinetic standpoint is that the loss of A over time will result in a gain of B over some time. Okay, so there's a couple of things that are important here. If we have a loss of A, we need to realize that loss is a negative term, whereas gain is a positive term. So the signs, the mathematical signs that we're going to put in front of a lot of these different variables as we start moving through today, you need to keep in mind when negatives keep popping up, we're usually talking about reactants, because reactants are lost in the course of a reaction, and products are gained in the course of a reaction. Now, the reason I mentioned equilibrium a minute ago is in equilibrium, you have exchange back and forth. Sometimes the products are going over to reactants, right? And in a case like that, you could have a loss of products and a gain of reactants. So in general, when we start outlining this at first, we're going to be talking about one directional reactions where A is going to B or reactants are going to products, right? And the other thing that we mentioned is time is going to be very important here. So when we talk about the rate of something, we have to look at the change, and specifically when we're in chemistry, it's the change of concentration over a change in time. And that's going to start talking about the rate of the reaction. So the way that we could define rate for the reaction written above is that we could say the rate is going to be equal to the negative delta A over delta T. Or we could also define it as delta B positive over delta T. So let's talk about what this means. This means that I can define the rate of my reaction as the loss of concentration of compound A over some period of time, or I can define the reaction as the gain in product B relative to its concentration over a change in time. So when we say or, we are saying equals. That means that this is the same as saying this over here. All right, so in a simple reaction like this, where A goes to B, this is fairly easy to understand. But this can rapidly continue to explode in terms of the amount of material we have to write out as we have A plus B goes to C plus D. And we also have a one-to-one stoichiometric ratio here, which is not always going to be the case. So let's take a look at that next. We're going to talk about the stoichiometric ratio. So what would happen if I said I have 2A for every 1B, because most of the time we don't always have a one-to-one ratio when we're talking about stoichiometric reagents. So in a case like this is going to be a little bit different than what we're used to with equilibrium, where we would normally say, oh, so take A and square that value. That's not what we want to do here. Because when we're talking about kinetics, we're talking about how quickly something depletes versus how quickly something forms. And if I have 2A creating 1B, that means that the rate of A would need to equal negative 1/2 the change of A over change in time, which is equal to the change of B over change in time. Okay, so if you think about this logically, every time there's 2A that are lost, I only get 1B in return. And that is why we put a half in front of the change of A, okay, because there's a heavier stockpile of it, so to speak, as far as the rate of B is concerned with its generation. So here is an example, and I'm actually going to ask people to try to solve this, and then we'll walk through it, all right? So here is a more complicated chemical equation. We have 4 stoichiometric moles of ammonia gas plus 5 stoichiometric moles of molecular oxygen gas, and that will go to 4 moles of nitrous oxide gas plus 6 moles of water in the form of a gas. So what I want the class to do, you can work this out individually here for a minute. I want you to write every single way that you could express this rate. So I want you to express the rate in relation to ammonia gas, to oxygen gas, to nitric oxide, and to water gas. So take 1 or 2 minutes and see if you can write out all the different ways that we could express this rate relative to each reactant and each product. And remember, the reactants should be negative when we associate values with them because we're losing them in the course of this process. So I'll give everybody a minute or 2 and then I will walk through this. And if you have a question, feel free to shout it out while we're working here. All right, so I'm going to start moving through this. It's okay if you're not completely finished with it yet. I think I forgot to mention in the announcements, I'm giving you additional time on your quiz today, not because it's super difficult, just to give you a little extra lot of time. So we are starting the quiz at 1:15. So I want to keep things moving through here. All right. So the way that I could have expressed the rate in a situation like this, I could say that the rate is equal to negative 1/4 delta NH3 over delta T. So that's how I could express the rate relative to ammonia, okay? Or I could set the rate equal to negative 1/5 the concentration or change in concentration of molecular oxygen over a given period of time. Or I could represent it as 1/4 without a negative because this is a gain in products, okay? The delta of the nitrous oxide over change in time. And again, I could put or. We have 1/6 the change in concentration of water, again, over change in time period. All right. So these are all related to one another through these various points. Now, this becomes useful when you know the rate of one of your particular reactants or the rate of the products being gained, and you'd like to find out the rates of the others, okay? Because I can relate them mathematically if I know the concentration of one and the time period that it happened over, or I can take it at a specific time point, like a tangent on a line, then I can set that equal to these others and I can figure it out based on these ratios. So let's move on then and take a look at a problem that's going to be slightly more complicated, where we're actually plugging some numbers into these and solving, right? So the next thing that I want you to do is let's consider the following reaction. We're now going to work with 4 nitrogen dioxide gas plus molecular oxygen, and that is going to go over to 2 of the dinitrogen pentaoxide gas molecules. Okay, now at time t, so we're taking a single time point. So at time, and we'll just call it some random time t, you measure this reaction and you find that the disappearance, or the rate of disappearance, for the oxygen is 0.037 molarity per second, right? So that unit is coming from, if you come back up and you look at the way we're setting all of these rates, it's a change in concentration, that would be molarity, over a change in time. That would be some amount of seconds as our standard unit of time. Okay, so at time t, the rate of oxygen's disappearance is found to be 0.037 molarity per second. Right, so we're going to answer 2 questions for ourselves here. A, we want to know what is going to be the rate for the appearance of the product Okay. And the second thing that we're going to answer, so part B here, is going to be what is the rate for the other product, I'm sorry, the other reactant here, and how quickly is it disappearing? So what is the rate for the NO2 gas disappearing? Okay. So let's start with A. What do we actually know in this scenario? Well, we know that the concentration of oxygen gas at delta T at a given point in time is negative 0.037 molarity per second. Okay. Now, in the problem, the rate is being given as an absolute. It's telling you that there's this much for the rate, but this is a rate that is a loss because it is a reactant going to a product. So I am putting in here, as I'm reading the problem, that this is negative. Okay. So remember, negative, when we're talking about a rate, there's technically no such thing as a negative rate, right? It has some value to it. The negative is simply stating that this is a disappearance. It's being removed from one side because we are going to have to set it equal to the product, which is going to be positive. So in order to get that math to work out, we have to understand that. All right, so for A, for part A, where we're looking at this, what we can do is we can say, all right, I know that I can set, this is going back to what we were working with earlier, I can set the negative rate of one of my reactants equal to the rate of the formation of product. Now I have to be careful here. So if I come up and I look, the oxygen has a 1, but the product has a 2 stoichiometrically. Now products are positive. I'm gaining product, so it would be a positive 1/2 because of that stoichiometric coefficient, okay? And it would be delta, and then the concentration of N2O5 over the change in time. And the change in time, we're taking an instantaneous point at time t right here. All right, so by setting this equal, here's what I can say. Now try to follow along. Because this negative here is in relation to this relationship, meaning the products to reactants relationship, it's going to be set equal to a negative 0.037, right? And then that would be equal to 1/2 the delta N2O5 over time t. All right, so the only thing I have to do then to find the concentration at an instantaneous point here is get rid of this half so that I can isolate this equation by itself. So in order to get rid of a fraction, I'm going to need to multiply by the inverse. So that means I'll take a 2, I'll multiply by 2 on each side here. Okay. So what this creates, if I'm going to multiply a 2 here, don't forget there's a negative out here. Okay, so it's going to be a -2 times -0.037, and that can be set equal to the expression over here, the delta N2O5 over time. And so this is rate of the product formation. Okay, now keep in mind it said what is the rate of the product formation. So this is going to be the answer here. So I take -2 times -0.037 and I get positive 0.074 molarity per second. And this makes sense because this value should be positive. It's a product. So I should see an increase in the product over that time period. Now, the next answer I see for B should be negative. And that's because when I look at this, it says, what is the rate for the NO2 gas? The NO2 gas is a reactant. I expect it to be depleted over time. So this is going to have to end up as a negative value as far as the rate is concerned. So let's go ahead and start looking at B then. So in the balanced equation, we have a 4 in front of that NO2. So when I want to get ready to set this equal, I'm going to say for problem B, I have -1/4, and that's going to be for the delta NO2 over delta T. And that is equivalent to a negative delta O2 delta T. So you can see why we ran through this first exercise where we said, let's just look at the reaction and say what the rates are when they equal one another. Because once we start going through this, we're going to have to set variables equal to one another in order to find it. We'll always have to set what we have or what's known, in this case the oxygen, equal to whatever other products or reactants we would like to find. Okay, so moving forward with this, what I can say then is I've got -1/4 delta NO2 delta T, and that is going to be equal to, now let's actually put the value in here, a negative, so keep that negative there, and then what is the value of delta O2 delta T? If we come back up, it's this value right here, -0.037 molarity per second. So I'm going to put here a negative, okay, just like before, 0.037 molarity per second. And same thing, I'm going to need to get rid of -1/4, so I'm going to need to multiply by -4 on each side. Okay? So keep in mind, if I've got a -4 and a negative, negative times negative becomes positive. So I'm going to rewrite this and say the rate of the nitrogen dioxide will be equal to a +4, because this negative and the negative from the other side that was brought over through multiplication of reciprocal makes it positive. And then I still have a negative inside of here due to the oxygen. Molarity per second. So all you have to do is solve that. And if you do, you find out that the rate of disappearance for the NO2 is going to be equal to -0.15 molarity per second. Okay, so here are the two answers. I didn't bracket or square this one. Okay, that would be for the formation of the product. You can see it's positive. You should always check yourself on your signs. And this would be the rate or loss of the other reactant based on the math here. All right. So I want to pause because there's a lot of plugging and chugging of numbers here and setting things equal to one another, and just see if anybody has a question before we start talking about the next subject. All right. So what I will go ahead and do then is I will delete the first portion up here, and we will get ready to move on to the next part of kinetics. So what we just went through is what's known as rate of reaction. So that's material for calculating the rate of reactions for any given piece of material, reactant or product that you might have. So the next thing we're going to do when we start working with rates, rates are typically set up with what's known as a rate law. So we're going to start taking a look at rate laws, and rate laws are going to be governed by the concentration of your materials, as well as what's known as a rate constant. So similar to a lot of the other subjects we've looked at with equilibrium, there are going to be constants that are involved in rate laws, and those constants, just like the equilibrium constant, will be unique to each individual reaction. So it's not a constant like Faraday's constant where it's going to be universal across the board. Every single reaction will have its own not equilibrium constant, its own rate law constant. All right. So let's take a look at another example here and tie it into rate laws. This time we're going to take fluorine gas plus ClO2. We'll have 2 of that. And that is going to yield 2 FClO2 gas. All right, now one of the things that we can do when we want to determine rates of reactions is we utilize rate laws experimentally. So what we're going to have here is we're going to have our experiment, okay, and we will have experiment 1, 2, and 3. Okay, so this is the reaction for this. And what we're going to look at in this experiment is the concentration of F2. We're going to look at the concentration of ClO2. And then we're going to look at the rate that results here. All right. Now, the way that you measure rate can vary. So sometimes it may be through color change, in which case you can use a spectrophotometer, similar to when we did the absorbance lab, in order to look for an increase or decrease in color over time. And you can associate that with rate. Sometimes you can use other instruments that can calculate or monitor how much concentration is in solution, and you can see how rapidly it's depleting or forming. So there's various ways that you can monitor the rate. Usually in an undergraduate lab, color change is the most common. Okay, so the concentration, and this is in molarity for each of these, the concentration for the fluorine in each case will be 0.10 in experiment 1. It will be 0.10 in experiment 2, and it will be 0.20 in experiment 3. Okay, the ClO2 is going to be 0.010 in experiment 1. It will be 0.040 in experiment 2, and it will be 0.010 in experiment 3. And the corresponding rates that come from these concentrations will be 1.2 times 10 to the minus third. It will be 4.8 times 10 to the minus third. And it will be 2.4 times 10 to the minus third. Okay. Now, what's important to note here, and this is the way you would always want to set this up experimentally speaking, is that we are holding one variable constant while we are changing another. So what we are doing In experiment 1 and 2, we are holding the fluorine concentration constant while we are allowing a fluctuation in the ClO2 concentration. And then when we look at experiment 1 versus 3, we are holding the ClO2 concentration constant while we are allowing the fluorine to vary. And that's important because if we have an initial experiment, let's call it experiment 1, we have a certain rate. So if I would like to see a change in rate, I'm going to need to know what is responsible for that change in rate. So if I change both of them at the same time, experimentally speaking, and then I say, oh, my rate has tripled, I don't know which one is responsible for tripling the rate. If they both are, if only one of them is, which one is the responsible one. So you have to break this down in a pattern like this, right? So let's work through some general assumptions here that we can make from our observations. So first of all, if we take a look at the fluorine, when the fluorine concentration doubles, what happens to the rate? So the fluorine concentration in experiment 1, and let's change colors for this so people can follow where I'm talking about, right? So I look at experiment 1, here's the fluorine concentration, 0.1 molarity. I look at experiment 3, where the fluorine concentration is 0.2 molarity. Now look at the ClO2, it's held constant. So any change I see in rate between experiment 1 and experiment 3 is solely due to fluorine. So when I look at this, I see 1.2 times 10 to the minus third goes to 2.4 times 10 to the minus third. I have seen a doubling in rate when I have had a doubling in fluorine concentration. Right? So that means that there must be a direct proportionality of fluorine to rate. So every time I double the fluorine, I'm going to double the rate. Every time I triple the fluorine, I'm going to triple the rate. That's the observation that I'm seeing based on this experiment. Is everybody comfortable with that so far? All right. So then, and I'm going to switch colors on you here so you can follow where I'm going. Then I take a look at how does the ClO2 affect this. So now I'm going to reaction 2, right? I see that there's a constant hold on the fluorine between 1 and 2, but I have a change in the ClO2 concentration. Specifically, it's a 4-fold change. So what happens to the reaction rate between experiment 1 and experiment 2? Well, 1.2 times 4 would be 4.8. So I also see a 4 times increase in rate when I have a 4 times increase in concentration. So these must have the same relationship that the fluorine did. There's a direct one-to-one relationship between the ClO2 and the rate of the reaction, right? Now, this is not always the case. Sometimes you might see that you double the concentration, but you quadruple the rate. So in a case like that, you don't just have a one-to-one correlation. It must be that the concentration has a squared value there. And we'll take a look at a more complicated example where that applies later. All right. So what we can do based on this is we determine what's called the rate law and the order of the reaction. So the rate law is going to state that the rate will equal a rate constant, which we will call little k, times, and we said that the rate is going to share a one-to-one relationship to the fluorine. So it's just fluorine, the concentration of fluorine, right, times the concentration of ClO2. This would be the rate law for this reaction. Now you can see what happens. If I hold this constant, the ClO2, and I say, let's multiply the fluorine times 2, and this is a constant. This is going to be what's known as the rate constant, which is unique to each reaction. Okay. If everything here is being held constant, if I can spell, okay, this is being held constant. If I multiply this by 2, this has to go up 2-fold. Okay, so this is the relationship that we're developing here through this experimental determination. So this is the rate law that I have here. Now, We were talking a second ago about the order. So the order simply is going to refer to the exponential factors that are found with each concentration. So if something is found in your rate law, I'm just going to use a common example A here, and it is raised to the first power, or there's an implied 1 there, we're going to call this first order. Okay. If I have something that is raised to the second power in my rate law, that would be considered second order. So you get the point here. If I had something that was going to be cubed, that would be considered third order in relation to the reaction. Now, when you multiply exponents, you add them together. So in this example, I have the concentration of fluorine being first order and the concentration of ClO2 being first order. So 1 plus 1 is 2. The overall reaction order is going to be second order. Okay. So the reaction order here is second order. And that's because if I take a look at this, the fluorine was first order, the ClO2 was first order. So when I combine them together, I get a second order reaction. All right. If I had a reaction where, let's say I had something that looked like this. This is a B. Okay. I could say for a given reaction like this, that A is going to be considered first order. B would be considered second order. And then the overall reaction, which I'm going to abbreviate RXN here, would be considered, would be considered third order overall. Okay. So that is where I'm going to stop the lecture at this moment, because we're going to get ready for the quiz in 5 minutes. So where we will pick up, and I'll probably post this to YouTube just so we get through the material in time. We're going to take a look at a more advanced breakdown of experimental determination of rate order and reaction order. So keep in mind that if you know concentration and you know rate, you can solve for a rate constant. So that is to say, if rate equals K times the concentrations, then you can also state that K, meaning I'd like to solve for my rate constant for a given reaction, is going to be equal to the rate at any given experiment time or divided by the respective product of concentrations, right? So that's just some algebra. Go ahead.
Sorry. I'm assuming that the exponent in this place is, again, the stoichiometric coefficient?
That's a very good question, and no, it is not.
It's not.
You would, yes, and you would think that it is based on everything that we've come up with for equilibrium, right? So if we come up and we look at this, if that were the case, we have a 2 in front of the ClO here, ClO2. And so I would expect then that the ClO2 should be squared. But the experimental data showed me that it could not be squared, because if this was squared, then that means if I make a 2 times increase in this concentration, 2 squared is 4. So that would be a quadrupling of the rate. All right, this is very important. The stoichiometric coefficients, they play into the rate as far as putting 1/2, 1/3, 1/5, etc. But when you get to this, it has to be experimentally determined. And that's a very good point, because we are so used to grabbing those and putting them as squared or cubed. That's not what happens here. We have to solve it experimentally. And we will take a further look at that later. Right? So I'm going to stop share, and I'm also going to stop recording.